Yeah. See about the realization of what is logic gate and realization of this logic gate by using NAND gate and NOR gate. Okay. So this we'll see. Okay. So basically, suppose AND gate means logic gates. So what are the logic gates we have? Like you have AND gate, OR gate, NOT gate. Okay, all this you have. Okay, so how to define these logic gates? How to define this logic gates by using in one sentence? Okay, so how to define these logic gates in one sentence? How to define? Okay, we'll see. Okay, yes. So yeah, first logic gates. Logic gates. Okay, so logic gates. Yeah. So what is my first gate? NOT gate. Okay. So NOT gate, how you depend? That means this is complement of input. Complement of input. NOT gate is nothing but complement of input. Okay. And next, you have what? Next gate is what? AND gate. AND gate. What is AND gate? Any input, any one of the input is low, the output is.
Sir, voice is breaking, sir.
Yeah.
Yes, sir.
Now, is it audible? Yeah, I think network issue. Next is AND gate. Okay, AND gate is nothing but what? Any one of the input is low. The output is low. The output is low. Okay. And next you have any one of the input is high. Any one of the input is high. The output is high. Okay. That is nothing but OR gate. Okay. And next NAND gate. Okay. OR gate. OR gate. Any one of the input is uh, high. Okay. Input is high. Okay. That is NAND gate. Okay. And next the output is high. Output is high. And next you have NAND gate. Which is what NAND and not is any one of the input. Okay, so not NAND gate is any one of the any one input, and one of input is low. The output is high. Just opposite of AND gate is nothing but an AND gate. And next you have NOR gate. NOR gate is nothing but any input, any one of input is high. High. Okay, the output is low. Okay, and next XOR gate. XOR gate is what we call as odd detector. So for odd number of inputs, you have the output. Output is for odd number inputs. Okay. So XOR gate is nothing but for odd number of inputs. Odd number of inputs. The output is high. The output is high. Okay. And next XNOR. XNOR is nothing but event detector. Event detector means even number of inputs. Even number of inputs. The output is high. Okay, even number of inputs. Okay, that means same inputs are there, same number of inputs are there, then output is high. Okay, so this you can divide. Okay, so suppose add gate, so first not gate, not gate. So what is the first symbol? What is the symbol? This is inverter. So here A, this is A bar, and here you have A Y. 0 means 1 and 1 means 0. Okay, this is not gate. Okay, and next buffer. Buffer means what? Buffer means so next buffer. Buffer means whatever the input you are giving, you are getting the output. So y equal to what? K. Y equal to A. So that means A. Y. 0 means you are getting 0. 1 means you are getting 1. This is buffer. Okay. And next you have AND gate. Okay. So AND gate is nothing but like for any that we are. So AND gate. So this is for AND gate. So A, B, and output equal output equal to A. Output equal to A. Okay. So if you see the truth table, two inputs are there. Okay. Two inputs are there. One is high. So
Sir, you have network issue, sir.
one the input and this is output. I think okay, I will rejoin. Okay, 1 second. I rejoin with my laptop. Other laptop. Okay. 1 second.
No, sir. It's not audible.
Now I'm audible.
Yes, sir.
You, anyone?
Yes, sir.
Yes. Can I audible? Am I audible?
Yes, sir.
Hello.
Yes, sir. It's audible.
Please tell me. Yes. Okay. Okay. Yes, I will start. 1 second. Yeah, I'll share the screen. Okay. Mm, Load. Okay, I'll share the screen. Okay, my screen is visible.
Yes, sir.
Okay. 1 second. Yeah. So what we are discussing, about logic gates, no? So logic gates. So next, so AND gate means. So we already seen the AND gate. Next, so yeah, yes. Next, I want to. Next, if I want to draw the OR gate, okay. So what is the OR gate? So this is the OR gate. This is the symbol. So A, B, and Y is equal to what? A plus B, and this is the A, B. If any one of the input is so any one of the input 0, 0, 0, 1, 1, 0, 1, 1. Any one of the input is high, the output is high. The output is high. This is OR gate. Okay. And next NOT gate. Sorry. Next you have NAND NAND gate. So NAND gate is so this is OR gate. OR gate. Next NAND gate. So NAND gate. So this is the NAND gate. So this is A, B, and Y equal to what? A, B whole bar. Okay. A, B whole bar. So we already seen that means truth table for NAND gate. Okay. So 0, 0, 0, 1, 1, 0, 1, 1. Okay. So what is NAND gate? NAND gate is nothing but any one of the input is 0, the output is high. And both inputs are high, the output is low. Okay. That is a NAND gate. And next you have NOR gate. Just opposite of that means NOR gate is nothing but OR gate followed by inverter. Okay. That is nothing but NOR gate. Okay, so this is A and B, and Y equal to what? ARB whole bar. Okay, ARB whole bar. So A, B, and output is what? Y. Okay, output is Y. 0, 0, 0, 1, 1, 0, 1, 1. Okay, just opposite. That means here any one of the input is high, the output is low. Okay, both inputs are high, the output is high. That is nothing but NOR gate. Okay, and next XOR gate. XOR gate. Okay. So XOR gate. What is XOR gate? This is nothing but OR detector. No. So OR detector means what? If like so this is the A XOR B. A XOR B. So you can write as what? A bar B plus AB bar. A bar B plus AB bar. Okay. So, so if you see the truth table, A, B, and output is Y. Okay, 0, 0, 0, 1, 1, 0, 1, 1. Okay, for odd number of inputs, both inputs are same, means the output is 0. For odd number of inputs, you have output as 1. Okay, so this is the expression for XOR gate. Okay, and next XNOR gate. XNOR is nothing but inverter. Means XNOR is nothing but XOR followed by inverter is nothing but XNOR gate. Okay, so this is you have a bubble A, B, and Y equal to what? A. This is the symbol A XNOR B, or Y equal to what? A XOR B whole bar. A XOR B whole bar. So if we see the truth table, A, B, and output is Y, 0, 0, 0, 1, 1, 0, 1, 1. If both inputs are same, the output is 1. Both inputs are different, the output is 0. Okay. So what is the expression for XNOR? A bar B bar plus A. A bar B bar plus A B. Okay. So this is the expression for XOR gate. Okay. Is this all gates are fine? Your response? Yes. Shall I move forward?
Yes, sir. Yes, sir.
Okay. Next you see. So next, so I want to implement. That means suppose if you consider like NOT gate is there. Okay. So suppose yeah, NOT gate is there. NOT gate. So NOT gate, I want to implement this inverter. Okay, you know that A and A bar. Okay, so I want to implement a inverter by using which gate? NAND and NOR. Okay, first you need to implement NAND and NOR. So by using NAND means what? Both inputs are tied together. So what you are getting? This is A. So Y equal to what? A bar. Okay, A bar. So Y equal to A bar you are getting. Okay, that means here A and A. A and A, this is equal to what? A bar. Okay, this is equal to A bar. And this is one representation. Second representation is I'll use the NAND gate. I'll use NAND gate. So this is A, and this one I need to connect to which one? Tell me. Anyone guess? I need to connect to which one? Logic 1 or a logic 0? I need to connect to logic 1. So that means Y equal to what? A and 1 whole bar. So this is equal to A bar. Okay, A and 1 equal to A. So we are getting A bar. Okay. So this I am implementing the NOT gate by using NAND gate. Similarly, suppose if I implement by using NOR gate, so how to implement so here inputs are tied together and given to NOR gate. Okay, so this is A. So A or A whole bar. This is equal to what? A bar. A or A whole bar equal to what? A bar. Okay, so this is the NOR gate, and this is one representation. Second representation is suppose here this one A, and here this I can give it to ground logic 0. Okay, so A or 0 whole bar, this is equal to what? A bar. Okay, this is second representation. The second representation I'm using these two representations I'm using when I develop the latch. Okay, when I develop the latch, there I'm using the second representation. Okay, so we'll draw with linear phase diagram that basic latch. Okay, linear phase diagram, basic latch. Okay, so there I will use this second case. Okay, and equivalency of gates. Equivalency of gates means is it fine? How you are representing this inverters with only NAND gates and NOR gates? Any doubt in this? Give your response so that I will move forward. Yes? Yeah. Any doubt? Shall I move forward?
No, sir. Yes, sir.
Oh, okay, okay, okay. Next you see. So next, equivalency of gates. What is this equivalency of gates? Okay. Equivalency of gates is nothing but suppose we'll discuss the means Boolean algebra. I think you have idea about De Morgan's law. De Morgan's law. So what is Demarcan's law? Like A or B, whole bar equal to what? A bar and B bar. A bar and B bar. So that means from this I can write NOR gate. This is A and this is B. NOR gate. So this is Y equal to what? A or B whole bar. This is equivalent to what? This is equivalent to bubbled and bubbled and. So this is A, B, Y equal to A bar, B bar. Okay, bubbled and. Okay. And next, one more Demarcan's like that. A, B whole bar equal to what? A bar plus B bar. A bar plus B bar. So from this I can say that this is nothing but what? NAND. NAND equal to what? Bubbled or bubbled or. Okay. Next, NOR. Okay. So NOR. So NOR means what? So NOR means, one second. Somebody is trying. Let them join. So NOR gate, yes, NOR gate if you see. So NOR gate, yeah. Yes. So, this is, sorry, this is NOR gate. This is NOR gate. This is NAND gate. NAND gate. Okay. So NAND gate if you see. So NAND gate is equivalent to what? NAND gate. So this is A, B, Y equal to A, B whole bar. Okay. So this is equivalent to bubbled R. Bubbled R. So this is A, B. Okay. Y equal to A bar or B. So that means from here I can say that NOR
Your mic got muted.
am I audible?
Yes, sir.
Okay. Yes. See here. So bubbled NAND gate is equal to bubbled NOR gate equal to bubbled and. Okay. One second. NOR gate equal to bubbled and NOR gate NAND gate equal to NOR gate equal to bubbled and NAND gate equal to bubbled R. Bubbled R. Okay. Is this fine? Shall I move forward? Waiting for your response.
Yes, sir.
Okay. Okay. Next you see. So how I need to implement this implementation using only okay, implementation using only NAND. Okay, how to implement it using NAND gate. Okay. Yes. We'll implement by using only NAND gate. Okay. Implementation using only NAND gate. How to implement by using NAND gate? First, write the logic function in the sum of product. Write the logic function in the sum of products. SOP. I think you have idea about SOP. SOP, sum of product. Okay. And draw the basic gates by using AOI logic. Draw the basic gate using AOI logic. AOI logic. Okay. Next. for AND gate, add the bubblet output and for OR gate, add the bubblet input. Okay. To compensate added bubble, added bubble, we need to add the inverter. Okay. Add an inverter. Okay. Add an inverter. Suppose any two inverters are connected in series. Any two inverters are connected in series. Okay. Just remove both of them. Okay. Both of them. And next, replace any remaining gates and inverters with the equivalent NAND and NOR. NAND implementation. Okay. So that means first you need to write the logic function by using sum of products. Okay, SOP, and draw the basic gates by using AOI logic. Okay, and or invert logic. And wherever the AND gates are there, you need to add the bubble at the output. Wherever the OR gates are there, you need to add the bubble at the input. So to compensate the added bubble, wherever you added the bubble, you need to add the inverter. So any two inverters are connected in cascade. Okay, so you need to replace. You need to remove that. Okay, and replace remaining gates and inverters with equivalent NAND gates. Okay, so is this fine? The procedure is fine. Shall I move forward?
Yes.
Okay. Yes. So next you will see. So next I will implement all the gates by using only NAND gates. Okay. First, what is my gate? First inverter. Okay. First is inverter. Okay. So I need to implement the inverter, not gate. Okay, not gate. See here. So not gate means here A. You are getting A bar. Okay, I need to implement with which one? So how to implement? So that means so this is the inverter, no? So inverter means so I can connect two inputs tied together, and I can connect like this. We already seen this is nothing but A and A whole bar equal to what? A bar. Okay, A and A whole bar equal to A bar. Next, AND gate. AND gate. AND gate, how to design like AND gate? This is the AND gate. Okay, this is the AND gate. A, B. Okay, Y equal to what? A. Okay, so wherever the AND gate is there, you need to add the bubble at where? Output. Okay, so output and next. So this is the these are the steps I am following. Okay, this is first step and second step. And wherever you add the bubble, you need to add the inverter at the output. So here you added the bubble. I need to add the inverter at the output. Okay. So I need to add the inverter at the output. And after that, so replace all the gates with the equivalent AND gates. See here. So this inverter I am replacing with NAND gate. So here A, B. Here you are getting A, B whole bar. Okay. Here A, B whole bar. Complement of complement is something but whole. We are getting A, B. So this is the AND gate. Do you got the concept? How I realized AND gate? Hello. Shall I move forward? Yes.
Yes.
Do you understood? Next you see. Next OR gate is there. OR gate. OR gate is there. So this is A, B, Y equal to what? A plus B. Okay. Wherever the OR gate is there, you need to add the bubble at where? Input side. Wherever the OR gate is there, you need to add the bubble at the input. So here A, B. Okay. Now, wherever you added the bubble, you need to add the inverter. Here I added the bubble. Okay. I need to add the inverter. Okay. And next, replace the added inverter with the equivalent NAND gate. So see here. So that means this is a NAND gate. And this is one more NAND gate inverter. Okay. So anyway, no need to add the, like wherever you added inverter. Okay. Okay. Next you see. So you already know that bubbled R equal to what? NAND gate. No? So this also NAND gate. This also NAND gate. A, B. So this is A bar. This is B bar. Here A bar and B bar whole bar. So if you apply DeMarcan's law, A bar whole bar plus B bar whole bar. So this is equal to ARB. ARB. Okay. So this is I'm implementing the with gate OR gate. You got OR gate? No? You got OR expression. Okay. So I'm implementing OR gate with this one. Okay. And next NOR gate means what? From here itself you'll get NOR gate. So that means this one I'm giving to one more NAND gate. Here I will get NOR gate. NOR gate. So here I will get what? ARB whole bar. ARB whole bar. Okay. So this is NOR gate. Okay. Till here, any doubt, any queries? So that I will move forward. Anyway, NAND gate means we are dealing with NAND gate only, no? NAND gate means we are dealing with NAND gate only. So this is NAND gate. This is NAND gate. Shall I move forward? Give a response so that I will move forward.
Yes, sir.
Okay. 1 second. Yes. Next, I want to implement XOR gate. Okay, XOR gate. I want to implement this XOR gate. How to implement this XOR gate? XOR gate. So XOR gate, if you see, so what is XOR gate? This is XOR gate. A, B, Y equal to A XOR B. This is A bar B plus AB bar. A bar B plus AB bar. Okay. So how to implement? This is nothing but my SOP, sum of product. Okay. First you implement with the AY logic and our invert logic. And our invert logic. So here you implement. So this is inverter and directly I'm giving and with an AND gate. And next this is A and this is AND gate. And this output is given to OR gate. Okay. This is A, B, and A, B. Okay. Next, what is the next step? Here I drawn this circuit. Wherever the AND gates are there, I need to add the bubble at the output. Wherever the OR gates are there, I need to add the bubble at the input. Okay. Now what happens here? I added the bubble. Wherever you added the bubble, I need to add two inverter that will cancel each other. No need to add the the inverters. Okay. So that means this is equivalent to, so replace all these things with equivalent NAND gates. So this is one NAND gate, and this one NAND gate, and NAND gate, and this is given to bubbled R equal to what? NAND gate. Bubbled R equal to NAND gate. So A, B, and this is A, and this is B. Okay. So here what I am doing, these two NAND gates are there, no? I am combining with one NAND gate and I am rearranging the circuit. Okay. How I am rearranging means, see here. This one is A and this one is B. So this one is A and B. Here, I'm giving with this one, and this NAND gate is nothing but this one, these two. Okay. Again, I'm giving to one more NAND gate. Okay. Now you see. So what is this? AB whole bar. Okay. By De Morgan's law, I can write what? A bar plus B bar. I can write A bar plus B bar. So this is A and A bar plus B bar whole bar. Okay. This is A and A bar plus AB bar whole bar. Okay. A and A bar equal to 0 from De Morgan's law. So you will get AR 0 equal to 8 itself. You get AB bar whole bar. Okay. Here also like this, you will get A bar B whole bar. You will get like this. If you do B and A bar plus B bar, okay, whole bar. Okay. So if you do, so this is the A bar B plus B and B bar whole bar. Okay. So anyway, this is 0. So you are getting A bar B whole bar. So this is what A bar. One second. This is what. One second. This is the AB bar whole bar and A bar B whole bar. Okay. Apply De Morgan's law. AB bar whole bar plus A bar B whole bar whole bar. Complement of complement is nothing but true form. So this is AB bar plus A bar B. So this is equal to AX. Okay. And next, this one, if you give it to one more NAND gate connected together, you will get X XNOR. A XNOR B. Okay. You know that A XNOR B whole bar equal to what? XNOR. Okay. So that means how many NAND gates are required to implement XOR gate? You require 4 NAND gates. How many NAND gates are required to implement XOR gate? You require 5 NAND gates. Okay, this is one of the interview questions they will ask. Okay, they will ask to realize XOR gate by using only NAND gates and only NOR gates, like that they will ask, and they'll ask how many NAND gates are required. In the written test also they will ask like how many NAND gates are required and how many NOR gates are required to implement XOR and XNOR, like that. Okay, so this is the implementation. Any doubt in this? Give response so that I will move forward. Yes. Do you have any doubt? Shall I move forward? Hello. Okay. Shall I move forward? Just a message in the chat box so that. Okay. 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 Next you see. So next I want to realize the implement by using what NOR gates. Okay. This NOR gates means what? NOR gate is only difference. What is the difference? Wherever you require like AND gates, where you have AND gates, add the bubble what? Add the bubble input. Input. Wherever the OR gates are there, add the bubble output. Output. Okay. So remaining procedure is same only. Okay. So this is the only change. Wherever the AND gates are there, you need to add the bubble the input. Wherever the OR gates are there, you need to add the bubble the input. Okay. So I'm implementing with which gate? NOR gate, only NOR gate. Okay. So why I'm implementing this NAND gate and NOR gate? These are nothing but what? Universal gates. Universal gates. Okay. So basically the gates are divided into how many types? So gates are divided into basic gates. Okay. Gates are divided into like you have basic gates. What are the basic gates? Basic gates are NOT gate, buffer, and OR. These are the basic gates. Okay. And next you have universal gates. Universal gates. Universal gates are NAND and NOR. NAND and NOR. And next you have special gates. Special gates. What are the special gate? Exclusive. Exclusive OR. Okay. This is nothing but inclusive OR. Inclusive OR. And exclusive NOR. Exclusive NOR. XNOR. Exclusive NOR. So that means why we call it exclusive NOR? Exclusive OR means if you observe the truth table of OR gate, what is the truth table for OR gate? 0, 0, 0, 1, 1, 0, 1, 1. So any one of the input is 1, the output is 1. This is the OR gate. So if you see the truth table for XOR gate, what is the output? So 0, 0, 0, 1, 1, 0, 1, 1. Okay. This is 0, 1, 1, 0. Okay. Till here both are same. Till here both are same. But which where you get the difference? For 1, 1, for OR gate this is 1. For XOR gate this is what? 0. That's why we call as this is inclusive OR gate. This is exclusive OR gate. Okay. Similarly, exclusive NOR is there. No. So first I'm writing the truth table for NOR gate. So NOR gate A, B, and output Y. Okay. So NOR gate means just opposite of OR gate. OR gate, no. Just you are giving the inverter. So this is 1, 0, 0, 0, 0, 0. Okay, this is NOR gate. XNOR gate means what? XNOR gate means here A, B, and output is Y. 0, 0, 0, 1, 1, 0, 1, 1. So this one, this is 0 and this is 0 and sorry, this is 1, this is 1 and this is 0. Okay. So that means from here to here both are same only. Inclusive NOR gate. This is inclusive NOR gate. This is exclusive NOR gate. So this here you'll get the difference. Here you'll get the difference. Here for 1, 1, you are getting the output as 1. Here 1, 1, output is equal to 0. Okay. That is the only difference. Okay. So these are the gates you have. And next we'll see the, so these are the universal gates. That's why I'm implementing by using all the gates by using, if you can implement any circuit by using these universal gates. Okay, that's why we call it universal gate. Suppose inverter is there. Inverter we already seen. A bar. So input is tied together and it is given to NOR gate. Here A plus A whole bar. Okay, this is equal to A bar. Okay, A bar. And next OR gate. OR gate you see. So OR gate means wherever the OR gate is there, you need to add the bubble at the output. Okay. And wherever you added the bubble, you need to add the inverter, no? So you need to add the inverter. So here. So you added the bubble, you need to add the inverter and replace all the gates with the NOR gate. So that means here this is NOR gate followed by NOR gate. Okay. So this is AB. ARB whole bar. So this is ARB whole bar. This is equal to ARB. ARB. Okay. And next AND gate is there. So AND gate. Okay. Suppose AND gate. Let us take AND gate. So for the AND gate, you need to add the bubble at the input. You need to add the bubble at the input. Wherever you added the bubble, you need to add the inverter. You need to add the inverter, and this is bubbled and replace all the gates with the respective NOR gate. Yeah. So see here. So this is the NAND NOR gate. Okay. So this is A bar, and this is B bar. A bar plus B bar whole bar. So A bar whole bar and B bar whole bar. So this is equal to A. You got NAND gate. Okay. So I'm realizing all the gates by using only NOR gates. Okay. And next you see. So I'm realizing NAND gate. Okay. How to realize NAND gate? I think from here itself I will get, you will get, no? So from here itself, this output is given to, yes, this output is given to one NAND gate, one NOR gate. You'll get what NAND gate, AB whole bar will get. Okay. And next, NOR gate anyway, we are erasing with the NOR gate only. Okay. And next, XOR gate. XOR gate. Okay. So how to realize XOR gate? XOR gate. First, this is XOR gate. A, B, by equal to what? A XOR B. Okay. A XOR B. This is equal to A bar B plus AB bar. A bar B plus AB bar. First, you draw with the normal AOI logic. So this is inverter and directly connected with the AND gate. And this is inverter. Okay. So this is A, B, and A, B. And this one is connected with OR gate. OR gate. Okay. Wherever the AND gates are there, you need to add the bubble at the input. Wherever the OR gates are there, you need to add the bubble at the output. Okay. And wherever you added the bubble, you need to add the inverter. You need to add the inverter. Just I am following the steps only. Okay. That steps I am following. Okay. Next, here this one. And here this is the bubble. And here I am adding the inverter. And this is the AND gate. Okay. And next, this is the NOR gate. Here also I need to add the inverter. Okay. And two inverters connected in cascade or in series, you can cancel each other. Okay. You can cancel each other and replace equivalent that gate. Bubbled are equal to what? NOR gate. And here bubbled are equal to NAND gate. Here also I need to add the inverter. No? Here also I need to add the inverter. Okay. Okay. That means this one is connected like this. Okay. And next here also I need to connect like this. And this one is NOR gate. And this is one more NOR gate. One more NOR gate. Okay. So that means I'm just so I'm connecting and combining these two NOR gates. Okay. And I'm rearranging the circuit. How I'll rearrange the circuit? Here you see. So from here I will get both XOR and XNOR. Okay. So I'm doing XOR, no? XOR. Just I will combine these two and I will rearrange the circuit. So how I'll rearrange the circuit? Yes. Yes. Somebody messaged me. 1 second. Yes, yes. We'll provide at the end of the month. We'll provide the certificate. Yeah. So here, this is one more NAND gate. Okay. So this is what A, B, A or B whole bar. This is equal to A bar and B bar. Okay. This is nothing but A or A bar B whole bar. So you have absorption law. Okay. A bar B bar. What is absorption law? A or A bar B equal to what? A or B. Okay. So this you can write as what? A or B bar whole bar. Okay. A or B bar whole bar. So if you apply De Morgan's law, A bar B bar for, I'm applying this De Morgan's law, you get A bar B. Okay, A bar B. Okay. And next, here also I need to use one more NOR gate. One more NOR gate. That is inverter. And similarly, here if you see, so that means B are A bar, B bar, whole bar. So this you can write as what? B plus A bar, whole bar. Okay. So if you apply De Morgan's law, B bar, A bar, whole bar. Okay. So this is AB bar you will get. AB bar will get. Okay. So here if you see A bar B plus A bar B plus AB bar, whole bar you will get. Okay. So here A bar B plus AB bar, whole bar, whole bar. So this is equal to A bar B plus AB bar. Okay, this is equal to A XOR B. A XOR B. So A XOR B, you got XOR gate. From here itself, you will get XNOR C here. A XOR B whole bar. This is nothing but complement, no? So complement is nothing but XNOR gate. Okay. So that means A bar B plus AB bar. Okay, this is equal to what? A bar B bar plus AB. Okay, how will you get this is whole bar, no? Just you apply De Morgan's law. A bar B whole bar and AB bar whole bar. So this is equal to A bar whole bar plus B bar, A bar plus B bar whole bar. Okay, so this is equal to A plus B bar, A bar plus B. So if you write A and A bar plus AB plus A bar B bar plus B and B bar. Anyway, this is 0 and this is 0. So this is equal to what? A bar B bar plus A. You will get this. Okay. So like this, you need to implement by using only NAND logic gates, by using only NAND gates and NOR gates. Okay. So just you can implement the logic function also. So this you can do as task. So any doubt is there, we can discuss in the next class. So y equal to this I am giving as task A bar plus BC bar. Implement by using only NAND gate and a NOR gate. Boolean equation. This is nothing but Boolean equation. Boolean equation. Okay. This is first one. Second one you see. Second one, suppose like logic diagram is given. Okay. Let us take this logic diagram. A, B, C, D. Y equal Y. Okay. So this implement this circuit also by using only NAND gate and NOR gate. NAND gate and NOR gate. Okay. So this is the implementation by using only NAND gate and NOR gate, and the logic gate, whatever the logic gates are there, implemented by using NAND gate and NOR gates. Yeah. Yes.